Okay, this is Dr. Proda at UC Merced. I'm going to do a mechanism video on the Dieckmann condensation. And the Dieckmann condensation is an intramolecular Claisen condensation. That's all it is. And we're going to do this diester, which has 6 carbons in totality, this diethyl ester. And with sodium methoxide ethanol, I'm going to do an aqueous workup step to make this 5-membered beta dicarbonyl. So this guys are beta keto ester, and that's why it's a Dieckmann condensation. It's like the analog of the Claisen, but in intramolecular process. So in the first step, you're going to use sodium methoxide and ethanol and deprotonate one of the alpha sites. I'm going to deprotonate this one first. So your base, sodium methoxide, is going to deprotonate it. In this case, methoxide minus is going to be our base. 1, 2, 3, 4, 5, and then that will give us the anion or enolate. So I'm going to draw it as the enolate again. So this will deprotonate that hydrogen to give you the enolate. Yes. Of course, it's an equilibrium process to give you the enolate. And of course, there's multiple resonance structures that you can draw for it. And that will give you plus ethanol as the byproduct, and that's why we buffered it with ethanol, because you're generating ethanol after each deprotonation event. Okay, so from the anion portion, the way you can tell that you got a 5-member ring as a product, just in case it would come up as not a mechanism type problem, you always go from your nucleophile to your electrophile, starting at calling this carbon number 1, for example, 2, 3, 4, and then this carbon, which is your electrophile carbon, is number 5. So there's a number of ways of doing the arrow pushing, but that's how you get your 5-membered ring. This is your nucleophile portion, and that's your electrophile portion. So this enolate will kick down to form a double bond, and this pi bond will then attack this carbonyl. Will wrap around and attack that carbonyl, and we'll kick up the electrons onto the oxygen atom to now give you your 5-membered ring. So that will give you your ethoxy group on the outside. So you basically are filling in. Don't forget that this carbon number 1 is not your reformed carbonyl carbon. It's one and the alpha site right next door to it. So that's your alpha cardinal. So don't forget that. The cardinal mistake is that people say that this C double bond O is directly attached to the ring, and you sort of exceed the valency or don't end up writing the correct structure. So you go to your alpha carbon, which is carbon number 1, as I've labeled it. It doesn't have to be carbon number 1, that's just arbitrary. And then you're going to get carbon number 2, 3, 4, 5. So this is 2, 3, 4, and 5. And at number 5, you're going to now not break the carbonyl and form an O minus, your tetrahedral intermediate, and O ethoxy. And so what you're going to get at this point is kick out of a leaving group and reformation of the carbonyl bond. So you've got an O ethoxy group. This will reform a double bond and then kick out the O ethoxy group. So you're going to get ethoxide minus as the byproduct, more ethoxide minus, plus that of your ester compound. And now you form your carbonyl. So just like when we did the Claisen condensation, you're not completely done with your step 1 that I have on the board here still. I'm going to erase in a second. You're almost done. You have to do a deprotonation of the beta keto ester because of pKa arguments. So what will end up happening is you're going to do a deprotonation and then a reprotonation, which seems like a waste of time, but it actually is what happens in, that's why you need an aqueous workup step. So from the beta keto ester, to finish off step 1, you're going to get this deprotonation of this hydrogen right here of your beta keto ester, and that we're using your ethoxide minus. So to complete step 1, this is what is going to go to completion, is you're going to deprotonate using that hydrogen here and form an anion at that carbon. I'm going to do it using forming the enolate, but you could have formed the carbanion as well. So then this gets kicked up to the oxygen to then give you this enolate. So the equilibrium favors the right-hand side by quite a bit. And so you're going to get ethoxide and an enolate, which you can, of course, draw it in various other resonance forms. This is just one of them. And you're going to generate more ethanol. So normally ethanol is not strong enough to protonate this because it's just going to favor the enolate formation. So, or one of the enolate structures. So then we're going to move on to a second step, and then the last step is going to be the aqueous workup with H3O+. So it's a simple protonation of the alpha carbon using that of H3O+ to give you more H2O plus your beta keto ester product. So now you've reprotonated at the alpha site to give you this beta keto ester product. So now that's it for this mechanism. It's an intermolecular Dieckmann condensation, is the intermolecular Claisen condensation.